Okay, so welcome again to the live session of characterization of construction materials. Today we will be discussing about the surface area measurement techniques. So without further ado, let me try to share the screen. Okay, yeah. Is my screen visible to all of you?
Yes, ma'am.
Okay, thank you, Pratiksha. So we have three attendees. Okay, okay. So you all know how the live session goes on. I'll share a question with you through the presentation. I'll also wait for the answers from you through the chat box. So please feel free to express your opinion and feel free to tell what the answer is, whether it is right or wrong, through the chat box. So I'm not delaying it any further. Let me show the question. Okay. So this is a very easy one. As the fineness of the sample increases, its reactivity dash. So what happens to the reactivity of the sample when the fineness of the sample increases? Reactivity increases, reactivity decreases, or reactivity stays the same. So what happens when the sample fineness increases? Anyone? Anyone in the chat box? What happens to the reactivity of a sample when the fineness increases? Suppose sample A and sample B are the same sample with same chemical composition. But what happens when A has a higher fineness? That is simply the question. Okay, I guess Pratiksha told A. I guess I'm not getting any other. Oh, yeah. No response further. So let's move to the correct answer. The correct answer is A. So as rightly told by Pratiksha. So here this line says that the particle size is 6 micrometer. Fineness increases. So 5 to 13 micrometer, 2 to 38 micrometer. So as the fineness of the sample increases, its reactivity decreases. Sorry, increases. Now, specific surface area is a surface area normalized by dash, normalized by volume, normalized by weight, normalized by area, or normalized by density. What is specific surface area? What is specific surface area? You all know about surface area. What is specific surface area? Okay, Pratiksha told it is surface area normalized by volume. Okay, anyone else? I guess that's it. If you do not respond, then this is how fast the live session will go. I can't help it. So, specific surface area is the area normalized by the amount or mass. So, surface area is having the unit of area like centimeter square or meter square or millimeter square. When it becomes specific surface area, it becomes area by mass, that is centimeter square per gram or millimeter square per kilogram, something like that. So they are normalized area. They are the area normalized by mass or weight. Okay, let's move to the next question. Calculate the agglomeration factor when the median volume diameter is 50 micrometer and the average diameter from the specific surface area measurement whatever is 5 micrometer. The median volume diameter is 50 micrometer and the average diameter is 5 micrometer. Calculate the agglomeration factor. Okay. Thank you, Pratiksha, for answering. Uh, she has told 10. So that is the correct answer. How did that become the correct answer? Because agglomeration factors is the ratio of medium volume diameter and the average diameter. So when the medium volume diameter is given and the average diameter is given, then median by average will give you agglomeration factor. So here 20, sorry, the question is different. So the question is 50 and 5. So 50 by 5 will be 10. So the answer is 10. So here the number is different, 20 and 10. So the question given was 50 micrometer was the median volume diameter, 5 micrometer was the average diameter. So median by average is 50 by 5, that is 10. So the correct answer is option D, that is 10. Okay, let me correct it here as well. Okay, so let's move to the next one. This is a true or false question. Powders should be sampled when they are in motion. State true or false. So when you sample powder for specific area measurements or something like that, they have to be in motion. They shouldn't be static. True or false? Okay, Javed response that it is true. Pratiksha and Mehna, any response from your end?
Ma'am,
Yeah.
I think I will go with true.
Okay. Okay, so let's move to the correct answer. So yeah, as Javed told and Mehna told, the correct answer is true because a powder, when it is not in motion, when it is static, obviously we know that sorry, the higher weighing samples or the sample fraction which is of higher weight tries to settle down, and the medium sized particle in the middle and very fine particle will be on the top. So what happens is that when you try to sample, only some of the fraction will come to you. It will not be uniform. So it will be either fine aggregate it is more, or maybe coarse aggregate is more if you're sampling from the bottom. So they have to be in continuous motion so that you will get a representative sample. Okay, let's move to the next question. Sieving is an ideal method for characterizing the complete particle size distribution of the cement sample. So you have a given cement, so you keep on sieving and then you get the particle size distribution. So is sieving the ideal method for characterizing the complete particle size distribution is the question here, whether that is a true statement or a false statement. Okay, Pratiksha goes with false. Fine, let's see what are the other responses coming. Anyone? Okay, so the correct answer is false, as rightly told by Pratiksha. Why? Because saving can be done only up to a particular size limit. It cannot be done below a particular size limit. So what happens? Cement has even finer materials. So how do we know the particle size distribution, full particle size distribution? We cannot use saving because saving can be done only up to a size, certain particle size. Yeah, and complete particle size distribution or PSD of the cement powder cannot be done through sieving because it has size even lower than the limit of sieve. So the correct statement is that sieving is not an ideal method for characterizing the complete particle size distribution of the cement sample. So let's move to the next question here. In laser diffraction, the laser passes through dash and get collected. So here is a particle and the laser passes through something and then it gets collected. So what does the laser pass through? It passes through powder, aerosol, emulsion or gel. Okay, so Pratiksha again responded that it is an aerosol. Okay, Javed also told aerosol, Pratiksha told aerosol. What about Mehna?
I will also go with them, ma'am.
Okay, so let's go to the correct answer. Correct answer is B, that is aerosol. So, aerosol is a suspension of fine solid particles in liquid droplets in air or gas. So, that is an aerosol. So, laser passes through aerosol and gets collected in the case of a laser diffraction experiment. Okay, Javed went with not aerosol. Javed went with emulsion. Okay, it's not emulsion. So, please be corrected. So, in emulsion, what is the case? Both the dispersed phase and the dispersed medium are liquids. Here we have powder samples in air or any other gas. So that has to be an aerosol. Okay. Let's move to the next one. So this is related to the Fraunhofer theory. So which of this A, B, C is true? All sizes of particles scatter with equal efficiency. Smaller particles scatter with higher efficiency. Larger particles scatter with higher efficiency, which is a true statement. Any response? Fraunhofer theory in laser diffraction. All sizes of particles scatter with equal efficiency. Smaller particles scatter with higher efficiency. Larger particles scatter with higher efficiency. So, what is the statement? Okay, so Javed goes with smaller particles scatter with higher efficiency, which is a true statement. So, Javed goes with B. Anyone else? What about others? Mehna, Pratiksha, and who else? Vijay Kumar. So, what is the correct answer?
I will go with B.
Okay. Okay. Since there are no more responses coming, let's move to the answer. So, Fraunhofer theory, all sizes of particles scatter with equal efficiencies. That was the assumption, or that was the statement given in the Fraunhofer theory. According to that theory, all the particles, whether it be small or big, they all scatter with equal efficiency. So please stay corrected, because you might think that the smaller particles diffract more, but according to Fraunhofer theory, all particles scatter with equal efficiency. Okay, let's move to the next question. Again, in laser diffraction, what are the particles assumed to be? Are they agglomerates? Are they aggregates? Are they spherical or are they colloids? Okay, Pratiksha goes with C, which is spherical. Anyone else? It's a very easy question. Anyone else? Okay, let's move to the correct answer then. Okay, so it's actually considered to be spherical, but that is an assumption. Not all the particles can be a spherical particle, but the in laser diffraction it is assumed that the particles are spherical in shape. This is a limitation as well. They are not actually spherical in shape, but we are assuming them to be spherical in shape. Okay, let's move to the next question. Okay, so suppose your particle is a cube of size 5 micrometer. Then calculate the equivalent diameter when the particle in your sample is a cube of size 5 micrometer. So I'll give you some time for this question. I hope you know how to solve it. You have a cube of size 5 micrometer. What is the equivalent diameter? Okay. So here the sample is a cube, or the particle in your sample is a cube. It has a size of 5 micrometer. Calculate the equivalent diameter. I'm not seeing any response from your end. Please try to figure it out, or else we'll discuss it.
Ma'am, could you please discuss because I am not knowing the answer.
It's okay. Let's give time to others also. Okay, Pratiksha goes with 6.2. Okay. What 6.2? Is it micrometer? Okay. Is there anyone else who wants to respond to this question? I'll give you just half a minute more, maybe. Okay, so let's discuss the answer. Yes, the correct answer is 6.2. You were right, Pratiksha. So, how do we calculate? Here, the side length of the cube is 5 micrometer. Volume of the cube is 5 cube. That is 125 micrometer cube, right? So, volume of a cube have to be equated to the volume of the equivalent sphere. You have a cube, its size is 5 micrometer. You know how to find the volume of a cube, side cube, that is 125 micrometer cube. Volume of a cube equals volume of a equivalent sphere. Then you equate both the volume. What is a volume of a sphere? 4 by 3 pi r cube or 1 by 6 pi d cube. That has to be equated to 125. That gives you d equal to 6.203 micrometer. I'll explain it again. So in your sample, you have a particle of size 5 micrometer, meaning one side of the cube is 5 micrometer. Now, if you have one side of a cube, how will you find the volume? Side cube, that is 5 cube. So 125. 125 micrometer cube is the volume of the cube. Now, what is the equivalent volume of a sphere? Same, 125 micrometer cube. So, what is the volume of a sphere? Formula 4 by 3 pi r cube or 1 by 6 pi d cube. Equate both. 1 by 6 pi d cube is equal to 125. So, d cube is equal to 125 into 6 by pi. That will be 750 by pi cube root. When you solve it, you get 6.203 micrometer. I hope that is clear. If at all you have any doubt, please let me know. Okay, let's move to the next question. Complex refractive index is related to refractive index and absorption coefficient as A, B, C, D. N equal to n minus ik, n equal to n plus ik, n equal to n into ik, n equal to n by ik. What is the equation which relates complex refractive index, normal refractive index, and the absorption coefficient? Okay, so again Pratiksha goes with A. What about Javed, Mehna, Vijay Kumar? Okay, let's move to the answer then. So the correct answer is A. There is nothing much to explain here. This is the equation which can relate the complex refractive index and absorption coefficient. So let's move to the next question. So here it's a bit tricky one, or it's not maybe. Your mixture is composed of particles A and B. Okay, just A and B. A has a diameter of 5 mm. These all are ideal cases. This will not happen in the reality. A has a diameter of 5 mm. B has a diameter of 2 mm. In proportions 1 is to 3 respectively. Diameter 5 mm, diameter 2 mm, in proportion 1 is to 3 respectively. The total number of particles is 100. Now, calculate the contribution of particle A to the volume of the mixture in percentage. I'll again explain the question to you. Your mixture has particle A and particle B. A has a diameter of 5 mm. B has a diameter of 2 mm, and A and B are in the proportion 1 is to 3 in quantity. Now, the total number of particles in your mixture is 100. Calculate the contribution of particle A to the volume of the mixture in percentage. I'll wait for 1 more minute before discussing the answer. Okay. So your mixture is composed of particle A and particle B. Particle A has a diameter of 5 mm and the particle B has a diameter of 2 mm. They are in proportions 1 is to 3. Now the total number of particles is 100. Say 100. So calculate the contribution of particle A to the volume of the mixture in percentage. Okay. Let's discuss the answer. So here, diameter of particle A is 5 mm. Diameter of particle B is 2 mm. Now, let me know if I have made some calculation mistake. Okay, let's see. Volume of the sphere is 1 by 6 pi d cube. So, volume of one particle A is 65.45 mm cube. Volume of one particle B is 4.18 mm cube. Number of particle A in the mixture. That is 25 because there is total number is 100. It is divided in 1 is to 3 as 1 is to 3. A, one part, B, three parts. Okay. So if A is 25, then B is 75. Thrice. Then only the total will become 100. Now, volume of particle A, how much it will be the total volume? 65.45 into 25. That is 1636.25 mm cube. Volume of particle B is whatever is here, 4.18 into 75. There, because there are 75 particles. So that is 314.16. The percentage contribution of particle A to the volume of the mixture is volume of particle A, that is 1636.25 divided by total volume. Total volume, how much it will be? 1636.25 plus 314.16. That will give you 83.89. So let me know if there is some mistake in the calculation, then we can recheck it. I don't know how 45 percentage Pratiksha got. Please do try and then let me know. So here diameter is 5 mm, diameter particle B is 2 mm, volume of sphere is 1 by 6 pi d cube. Then volume of one particle A is 1 by 6 pi 5 cube. Volume of one particle B is 1 by 6 pi 2 cube. Now the constraint is to know how many number of part. I have made a okay, okay, Pratiksha. Fine. So the how do we calculate number of each particle? Total is 100. It is divided in proportion 1 is to 3. If there is one particle of A, there has to be 3 particles of B, but the sum has to be 100. Okay, so 1x plus 3x is equal to 100, 4x is equal to 100, x is equal to 25. So particle A, there are 25 numbers, particle B, there are 75 numbers. So what will be the total volume? The number of particle into volume of one particle, right? So 25 into 65.45 for volume of particle A, and volume of particle B will be 75 into 4.18. So the percentage contribution will be volume of particle A divided by total volume. So what will happen if we are asking the percentage volume of B? Then volume of B divided by total volume. Then it will be 314.16 divided by total volume. 314.16 plus 1636.25. So the answer will be 100 minus 83.89 because there are only two particles A and B. So I suppose this calculation is clear for you. If not, please let me know. Okay, let's move to the next question then. Sieving can be used to calculate the particle size in the given sample when the least size is above dash. So before this, we told that for complete particle size distribution curve of cement, we cannot use sieving because it has a limiting size. So this question is about the limiting size. So it can be used if the particle size, least particle size is 11.2, 4.75, 75 or 37 micrometer. Okay, Pratiksha goes with 37. Anyone else? Any response? Any other response? Okay, Vijay Kumar goes with C. Javed also goes with C. Okay, thank you all for responding. Let's move to the next correct answer. The correct answer is D, that is 37 micron. So here, if you see sieving in air, it has a minimum range of 37 microns. Okay, so I hope that is clear because if at all your sample has a particle of size great lesser than 37 micron, then we cannot use sieving. Okay, let's move to the next question. The specific surface area is derived from the resistance to flow of air or some other gas through a porous bed of powder. Which technique is referred to in the statement? So, is it laser diffraction, or is it gas adsorption, or is it Blaine's air permeability, in which the specific surface area is measured from the resistance to the flow of air through a porous bed of powder. So our powder is kept and an air is made to flow or some other gas is made to flow through the powder and it faces a resistance. You quantify the resistance and then you get the specific surface area. So which method is mentioned here? Javed and Pratiksha, or just Pratiksha? Pratiksha goes with C. Blaine's air permeability. Okay, who else? Let's move to the correct answer. The correct answer is C, because in Blaine's air permeability, as the name suggests, it's through the easiness for the air to pass through a particular sample, we get the specific surface area of the particles which make the sample. So the correct answer is Blaine's air permeability. In the case of laser diffraction, obviously the laser has to diffract. In gas adsorption, the gases have to get adsorbed, nowhere the resistance to flow comes. So it is in the case of air permeability, that is Blaine's air permeability, the resistance to flow comes in the picture. Okay. Again, the next question is also related to Blaine's air permeability. The permeability is dash the particle fineness, directly proportional to or indirectly proportional to. No response. Okay, let's go to the answer then. The correct answer is A, that is directly proportional. The principle of operation is that the permeability of a bed of fine particles is proportional to the fineness of the particle. So they are directly proportional according to Blaine's air permeability test. So, next question. The vapor adsorption isotherm corresponding to cement. So, adsorption isotherms are different for different type of materials, and there are type 1, 2, 3, 4, like that. According to cement adsorption isotherm, which one uh, is more suiting to the cement adsorption isotherm? Vapor adsorption isotherm of cement. Okay, type 4, Vijay Kumar says. Okay, Pratiksha also goes with D, that is type 4. Okay, let's move to the correct answer. Yes, the correct answer is D. So, as shown here, type 4, mesoporous materials such as cement. It's not, so here, type 4 goes like this, it has a double curve like that. So, type 4 is the adsorption isotherm corresponding to cement. Let's move to the next question. Increase in the partial pressure leads to desorption. Increase in partial pressure leads to desorption. State true or false. So the statement says that when there is a partial pressure increase, then desorption occurs. What is desorption and adsorption? That first you have to think about and then answer. No more response. Okay. Let's move to the answer. The correct answer is B. See, just simply think, if you take some powder and then you apply it onto your palm and you apply pressure. No, this is not the correct way of explanation for partial pressure or adsorption. But just for your easiness to think, if you do like that, as you increase the pressure, powder might stick onto your palm. So, what is adsorption? Adsorption is the it's a contact, or it's the contact of a sample, contact of certain molecules to the surface of another material. It's a deposition of one type of material on the surface of other type of material. That is known as an adsorption. Desorption meaning they both get separated. Two samples, one sample gets adsorbed onto the surface and they both separates. That's known as desorption. So in the previously, when you thought like when the pressure applied, powder got stuck into your palm. Similarly, just imagine that when the partial pressure increases, it is easy to adsorb, not desorb. When you apply pressure, it gets stick. So it adsorbs and not desorbs. Okay, so let's move to the next question here. Dash isotherm is also known as Langmuir isotherm. Most of the questions are just direct type 1, type 2, type 3, or type 4. Dash isotherm is also known as Langmuir isotherm. Okay, B, Pratiksha A. Okay, so the correct answer is A, that is type 1. It's also known as just like this. It increases and then becomes a straight line kind of. So, or asymptotic to the x axis, relative pressure axis. That is known as a Langmuir isotherm. Type 1 isotherm, the first one here, is known as a Langmuir isotherm. Okay, let's move to the next question. Choose the correct statements related to the assumptions in BET theory. So, BET also is a technique which we use to find out the specific surface area. So, what are the correct statements? In BET, a molecule can evaporate even if it is covered by another molecule. Is that an assumption of BET? Now, number of layers are finite at saturation. Is that the assumption of PET? Now, this third one, only the uppermost layer of molecules in a multi-layer system, suppose there are so many layers of adsorbed systems, only the one at the uppermost layer are in dynamic equilibrium with the vapor. Is that the correct assumption? Now, the fourth option is that adsorption energy varies during the formation of the first layer. So, what are the correct assumptions in BET theory, or correct statements related to the assumptions in BET theory? Okay, Pratiksha goes with C. Just C, or anything more? Anyone else? Okay, so let's move to the correct answer. The correct answer is just C, because first line, molecule cannot evaporate if it is covered by another molecule. How can it evaporate? It is covered by another molecule or by another layer of molecules. How can it evaporate? So the first one is wrong. Number of layers are found to be infinite. So here, if you see the fifth option, at saturation, fifth bullet point, the number of layers become infinite. So here the option is finite. Option C is it's finite. So it's wrong. Now C is correct. Uppermost molecules are in here multi-layered adsorbate are in dynamic equilibrium. The last option is adsorption energy varies in the formation of first layer. That is also wrong because BET assumes that the adsorption energy is same or constant during the formation of first layer. Okay, let's move to the next question. So nitrogen is widely used as an adsorbate. It can measure surface area as low as 1 meter square, 1 square, 1 nanometer square, and 1 micrometer square. So, what is the limit of measurement of surface area for nitrogen gas adsorption? Okay, so Pratiksha goes with A. Anyone else? Okay, the correct answer is A. The current adsorption equipment can measure absolute surface area as low as 1 meter square using nitrogen. That is the limit up to which nitrogen could measure. Okay, this is the last question for today. As hydration progresses, surface area of the cement paste decreases. So, stay true or false. What happens to the surface area of the cement when it hydrates? Cement paste. It hydrates, and what happens to the surface area? It increases or decreases? The statement says it decreases. Stay true or false. Okay, Narasimharaju and Javed goes with B, false. Okay, the correct answer is B, false. So, what happens when there is hydration progression? Then more hydration products are formed, such as CSH gel. They have very high surface area. They have a layered structure. CSH especially has a layered structure, and it has pores also. So, the surface area will be much higher. So, as the hydration progresses in the case of a cement paste, its surface area also increases. So that was it for today. Thank you. And I hope we stop the recording.